Page 65 of the manual now. So we have this thing, we'll just go back, although you've probably just seen it. If you have a second order linear differential equation like this thing in black here, what you do is you write down what's called the auxiliary equation, this underlined green thing, the auxiliary equation. And it turns out that e to the power of a root of this times t is a solution of the differential equation. And it turns out you get all of them. Where is it written? Up here. Yeah, basically you get all of them. Where is it written? Yeah, so you get the two roots, say r1 and r2, and these two exponentials are solutions of the differential equation. And what you can do is you can multiply them by scalars, by constants, and add them together, and that's how you find all of the solutions. Now there's three different scenarios. One where the two roots are real but different, and then the real repeated, and then finally complex. So the easiest situation is when you've got two real roots that are different. So by the theory, it says that the solutions are, this is called the general solution. Now the general solution can capture all possible starting displacements and starting velocities. So say the roots are alpha and beta, so e to the alpha t and e to the beta t are solutions. Now you can get more solutions by multiplying solutions by constants. So if e to the alpha t is a solution, a constant times e to the alpha t is a solution. And you can also get more solutions by adding them together. So e to the beta t is a solution, multiply that by a constant b. And so e to the beta t is a solution. And it turns out that this is the general solution. This is all the possible solutions of the differential equation. So let's see an example. So first of all, you write down the auxiliary equation. So you take the coefficients 1 plus 3 and 2 and form a quadratic equation. So for example, 1r squared, which is just r squared, plus 3r plus 2. Now you could go to the minus b formula with this and find the roots, but this chapter is only worth 15%. Next chapter is worth 35%, and in the next chapter you have to actually factorize, not just find the roots. So we will do the factorizing. So the factorizing is the AC method. This is what I recommend. If you've no problem factorizing quadratics, if you can do them in your head and get them right, that's no problem. Otherwise, this is what I recommend. So you multiply the a by the c, the 1 by the 2, you get 2, and then look at all the factors of 2. Now 1 by 2, 2 you already have. Now can you make up 3r using a pair of those? Yes, you can, of course, because you can write 3r as 1r plus 2r. So we have r squared. I'm probably missing a 0 here. Well, actually, let's factorize it first. Okay, so I get r squared, and then using this over here, 3r is equal to r plus 2r plus 2. Take out the common factor out of the first two terms, which is r, and you're left with r plus 1. And then take out the common factor of the second pair of terms, such that you get r plus 1 again. So that would be plus 2 times r plus 1. And then take out the common factor of r plus 1, and you're left with r plus 1 times r plus 2. Now you're interested in solving, we mightn't always write it like, we mightn't always factorize it in one line like this, as we'll see. So you're interested in this equal to 0. So if you're interested in that equal to 0, you're interested in r plus 1 times r plus 2 equal to 0. That's the same thing, because the thing in the green is equal to r plus 1 times r plus 2. Now when are two numbers multiplied together giving you 0? That only happens when one of the numbers is 0. So we've either r plus 1 is equal to 0 or r plus 2 is equal to 0. The first one we can take away 1 from both sides, you get minus 1, and the second one you can take away 2 from both sides. So the two roots are minus 1 and minus 2. So these are real roots, they're real numbers, and they're distinct, they're not the same. So we get a solution given by e to the minus 1t. We get a solution e to the minus 2t. We also can multiply these by constants to get more solutions. And we can add them together, and it turns out that's all the solution. So the general solution of this differential equation is a e to the minus t plus b e to the minus 2t. Now, if in addition, and we will do this next week, you say what the value of y is at t equals 0, and maybe the value of dy dt at t equals 0, then you can find the values of a and b that will make that so. Okay. This is now more technically demanding than I think anything you've seen before, and it's going to get more technically demanding in the next chapter. So now here, there's something interesting about these. So if we look at, say, e to the minus 1t and e to the minus 2t. So here we're going to take three things. So this, now I don't know is this exactly those numbers, but you can imagine it is. So this would be e to the minus t plus e to the minus 2t. Now, of these two terms, the e to the minus 2t goes to 0 faster. Now, why is that? Let's draw a little picture. So exponential functions, at t equals 0, they're equal to 1, and then they get bigger. So they go something like that. And if this is e to the t, well, e to the 2t grows even faster. So for example, we'll just give you a little example of this. E to the, say, power of 10 is approximately 22,000. So that's, I'm saying that's, this is t equal to 1, excuse me, this is supposed to be t equal to 10, say. And then e to the 2 by 10 is e to the 20, which is, oh god, I can't even really see it, 10 to the 3, 10 to the 6, 10 to the 8, it's approximately 5 by 10 to the 8, it might be 10 to the 7, 10 to the 8, but something like that. So the e to the 2t is much, much bigger. Now, if you're comparing e to the minus t versus e to the minus 2t, what does a negative power mean? It means a division. So you're comparing 1 over e to the t versus, we'll move this, 1 over e to the 2t. And which one is, well, what's going on with these? Now this, the 1 over e to the 2t is 1 divided by a bigger number. So this goes to 0 fast. And the other one goes to 0 slow. Well, it actually goes to 0 quite fast, but relatively slow. Let maybe say slower. So if I'm looking at this thing here, so the blue curve is the e to the minus 2t, that goes to 0 fast. And then the green one would be the e to the minus t. So if you look at the sum, the red term, a part of that goes to 0 quite quickly. So this bit goes to 0 quickly. And then the other term takes a bit longer. So see the way the red, look at the red curve now, the e to the minus 2t plus e to the minus 2t. See the way it quickly decreases down to, say, around here. So this is like the quick phase, and this is, say, the slow phase, something like this. And then it kind of slows down. Have you ever seen a door close? Where, let me try and draw a door here. This is supposed to be the door frame. No, this is going to be the door. The door is going to go like that. So the door, if you open the door, it closes quickly and then it kind of creaks. The last bit is really, really slow. So it's a door, it closes quickly, and then it kind of takes ages to close. If you think about doors with door closers, you've surely seen this before. So this is an example of something that we're going to see later on. This would correspond to, in context, overdamped. And essentially what happens is that the damping is too strong, so the door is moving, and it picks up a good bit of speed, and when it picks up the speed, the damping really kicks in. But what happens is the damping kicks in so much, it basically stops the door before it's closed. And then where you are is, so what the slow bit represents is the displacement is very, very small, and so the spring force is very, very small. And so you get this kind of behavior of the door closing quick and then slow. Okay, so whenever we see these two exponentials, one of them is going to go to zero quickly and the other one is going to go to zero slowly. We're going to see that later on. Okay, that's the easy case. Now this one is a bit harder. In this case, the b squared minus 4ac is 0. The auxiliary equation is only one root. Now, if you wanted to say that the solution should be ae to the alpha t plus be to the alpha t, then this would be a mistake, because this actually is only a one-dimensional solution. The theory says there must be two solutions. So a more practical reason is that this couldn't be the whole story, because there's, like, even with the door, think about the door, there's the initial position of the door is going to play a role eventually. So how far open the door is, and the initial speed of the door. And if this is your solution, that can't simultaneously satisfy initial conditions about the displacement and an initial condition about the velocity. There has to be two different things. Okay, so what we do, it's not clear what to do, but we go back to the principle that says there's two solutions. If we find two, we're done. So we're just going to chance our arm by taking the second thing, this yoke, and multiplying by t. It is chancing our arm, but the theory says if it works, we're done. So let's see, does it work? So take our, I'll do this quite quickly because this is kind of more theory than you need. I think it's nice to see how it works though. So we've got a times second derivative plus b times first derivative plus c times the function we're looking for equal to 0. Now we know that where alpha is a root of AR squared. So where is this alpha coming from? So this alpha a root of the auxiliary equation, which is AR squared plus BR plus C, which is to say that if you substitute in R equal to alpha, you get 0. So A alpha squared plus B alpha plus C is equal to 0. We're going to be using that afterwards. Okay. So it's set up that AE to the alpha t will work. Now we're going to try BT e to the alpha t. So see, does it work? So we're going to have to find the first and second derivatives of this, and we should use the wrong pen. We should use the product rule, UV. So now we're going to be really stuck for space underneath C. Oh no, we're going to be okay, I think. So let's find the first derivative. So the first derivative of this function is the first thing, which is bt, times the derivative of e to the alpha t. Now you go into your tables, the derivative of e to the alpha t is alpha e to the alpha t. So that's the first thing by the derivative of the second thing, plus by the product rule, so I'm using this UV business, e to the alpha t times the derivative of bt. Now b is a constant, so I fix it. And what's the derivative of t with respect to t is 1. So it's this thing. Okay, and now we're going to differentiate a second time. We can tidy this up, but it doesn't really matter. I'm going to take maybe all of this. Well, maybe this to be u, this to be v, so I need a second product rule here. This is easier because it's just a constant times e to the alpha t. So the second derivative is do a uv on this one. So u is bt times the derivative of the second thing. So fix the alpha, and what's the derivative e to the alpha t? Well, again, it's alpha e to the alpha t plus the second thing, which is alpha e to the alpha t times the derivative of bt. Fix the constant b, and the derivative of t is 1. And now plus differentiate the second term. So fix the constant b, and the derivative of e to the alpha t is alpha e to the alpha t. So I have the original function that I'm trying to chance my arm with, this. I have the first derivative that I could tidy up, but I don't really care because I'm not going to go through it all. And then this is the second derivative. And we're going to see if we put these yolks, this in there, this in there, and this in for the second derivative, do we get a solution? And if we do, we're done. So you can bang those numbers in. They might look a little different here, but I promise you that's just after a simplification. And you can rewrite this as follows. So there is, you can take out the bt e to the alpha t, bt e to the alpha t, bt e to the alpha t, bait, bt e to the alpha t, what's left? So there's an a alpha squared, b alpha, and I think just a c, so that's that. And then the other thing, take out beat, so b eat, b eat, and there's none there. So if you do that, you're going to have 2 alpha by a, 2 alpha by a, and b. So we know, we've written it on the previous page, this is equal to 0. And if this is to solve the differential equation, remember we want it to be equal to 0, this thing has to be equal to 0 as well. So as the root is repeated, and we can actually show, and this would have been done in a previous lecture, if the root is repeated, it's equal to b minus 2 alpha, and that actually means that this bit is equal to 0 as well. So it turns out that if alpha is a repeated root, a e to the alpha t is a solution, but also this one. Now the way I'm going to explain this, because we're going to use this again, is something like this. So the general solution in this case, so you get e to the alpha t times a plus, now what you want to do is b e to the alpha t. That cannot work because those two solutions are basically the same thing. So you change this one by multiplying it by t. Now you will see that again later. Okay, so we'll do an example like that. The displacement of a damped harmonic oscillator is given by this. Solve for the displacement. So the first thing we do is we find the auxiliary equation. So what we want, the auxiliary equation is, so this is 1, we want to solve r squared plus 6r plus 9 equal to 0. Now what I'm going to do is I'm going to factorize the r squared plus 6r plus 9 first. You don't have to do that in this chapter, but we're going to have to do it in the second chapter, so we may as well start doing it. So off we go. So r squared plus 6r plus 9, let's factorize this. So we'll use the AC method. So you multiply the a by the c, the 1 by the 9 is 9. You look at all the factors of 9, 1 by 9, 2 doesn't go, 3 by 3. And can you make up plus 6r using a pair of those? Yes. Okay. So we end up with, this is equal to r squared, and then the 6r is equal to 3r plus 3r plus 9. Then we take the common factor out of the first two terms, which is r, and you're left with r plus 3. And then you take out something common out of 3r plus 9 that leaves r plus 3 again. That would be 3. And then you take something common out of these two. That would be r plus 3. Now you will have to factor in chapter 3. So we're practicing now. If you can do this, if you can get from the r squared plus 6r plus 9 and do the factorization in your head, no problem. okay, as long as you're getting it right. So if you want to get r squared plus 6, 9 plus 9 equals 0, that's the same as saying r plus 3 times r plus 3 equal to 0. Two numbers multiplied together, r plus 3 times r plus 3 giving you 0, then the only way that can happen is if r plus 3 is equal to 0 or r plus 3 is equal to 0. Take away 3 from both sides, you get r is equal to minus 3, but you get minus 3 twice. So this is a repeat. Now they're real numbers, but they're repeated. So that's this case. So how do we write down our solution? Now it's not y here, by the way, it's going to be x. So x, the g stand, the general, it means that all possible initial displacements and velocities can be captured with this solution. Function of time equal to. So e to the minus 3t is a solution. I can multiply that by a. I'm tempted to write b times e to the minus 3t, but I can see that these two solutions are actually the same. So I change the second one by multiplying it by t. Okay, now one of the things that happens with this, as we'll see later on, is that you don't have the fast and the slow. So do you remember the fast and the slow is this thing, the door closing quickly and then slowly, where you have the different powers of the exponential, say minus 1t and minus 2t. In this one, both of them have the same speed, as it were. Now the t kind of complicates things, but we won't go into that. But basically they're the same speed. So both of these go to 0 pretty much at the same speed. So this is a very well, if it's a door, it's a well-designed door. It closes kind of in one go without going fast first and then slow. Now we're going to have serious crack with the complex roots. Now for me, it's very interesting to see how the complex powers work. So I'm going to go through them. But then at the end, once we get through the theory, you'll just be using the thing. But for me, I have to teach it in the interesting way and kind of explain as much as I can without explaining absolutely everything. So in this case, you have two complex roots, p plus iq and p minus iq. So the two solutions are this yoke and this yoke. So the solution is going to be general solution a e to the p plus iq t plus b e to the p minus iq t. Now the problem with this is, what the hell is, like, that I is the I squared equal to minus 1 is this imaginary number. And like, it's like, oh, I have a door closer and I'm getting complex numbers. What? So, okay, so the first thing is to deal with the p plus iqt. So we're going to assume that normal properties of indices hold. So if I multiply this thing out, I get e to the power of pt plus iqt. And like, if you remember your kind of laws of indices, if you have a sum of powers, it comes by multiplying powers together. So this is the same as e to the pt times e to the iqt. Now the e to the pt is actually no problem. We know exactly what that is. So that's not an issue. We just have to know what e to the iqt is. Now what we're going to do is we're going to figure out what e to the I theta is. Now why am I using theta? That will become clear. So normally often in a class, if you're in front of me, I'd say, oh, how do you think it's going to work? I'm not even going to ask that. I'm just going to show you. And I'll go fairly quickly. I just think it's really cool. So we're going to take advantage of the philosophy that the Taylor series should simplify this. So if you remember your Maclaurin series that we did at the end of last semester, we would have shown that the Maclaurin series of e to the x is equal to, so I get e to the x is equal to 1 plus x squared over 2 plus x cubed over 3 factorial plus x to the 4 over 4 factorial plus x to the 5 over 5 factorial. And I think we'll do just one more, x to the 6 over 6 factorial plus. Now, how could you possibly come up with this yourself? Not very easily, but we said that the Taylor series was a way of making something that was complicated easy. Now, easy means addition and multiplication, and that's all we have in the blue, but you can't make everything that's difficult easy. So how you pay back as such is you have an infinite sum here. So let's see what happens anyway. We'll just bang in I theta and see what happens. So e to the I theta should be 1 plus, so instead of x, I'm putting in I theta plus I theta squared over 2 plus I theta cubed over 3 factorial plus I theta to the 4 over 4 factorial plus I theta to the power of 5 over 5 factorial plus I theta power 6 over 6 factorial plus dot dot dot, go on forever and ever and ever. Now you're possibly more confused than you were, that's okay. This is really cool maths as far as I'm concerned. Now let's look at the powers of I. So I, we don't say anything about just I on its own, but we said that I squared is equal to minus 1. Now what would I cubed be? Well, that would have to be I squared by I. And I squared is minus 1, so I cubed is minus I. And what about I to the 4? Well, there's different ways we could go about it, but it should be definitely the same as I squared. And I squared is minus 1, so it should be minus 1 by minus 1, which is plus 1. And then what about I to the power of 5? Well, that's going to be I to the 4 times I. And I've already shown that I to the 4 is 1, so that's I. And what about I to the 6? Well, that should be I squared times I to the 4. I know what I squared is, it's minus 1. And I to the 4 is 1, so it's minus 1 by 1, which is minus 1. And you get that the pattern will just keep repeating. So the pattern of the powers of I are, it starts with I, minus 1, minus I, 1. I, minus 1, minus I, 1. So just the pattern is going to be 1 to I to minus 1 to minus I back to 1. And you can actually draw a picture of that. But I won't do that because this isn't a class about complex numbers. So what we're going to do is we're going to separate this Maclaurin series, the e to the I theta, into the real and imaginary parts, e to the I theta. So take all the bits that are real. So we get the number 1 plus. So think about I theta squared. That'll be I theta by I theta. The I by the I gives you I squared as minus 1. And so you get minus theta squared over 2. Now, what about the I theta to the 4? So that'll be I theta by I theta 4 times. You get 4 i's multiplying together, I to the 4, which gives you 1. And you're left with the theta to the 4 over 4 factorial. And then the next one, the I theta to the 6, you can show that that will give you theta to the 6 over 6 factorial. Okay. And actually, I've drawn that too fast. And of course, this pattern will go on and on forever. Plus, now take the i's out of the imaginary ones. So the even powers of I give you real numbers and the odd powers of I give you imaginary numbers. So take out the I out of the imaginary. So the first one is I theta, you're just left with theta. Then look at the third term. You're looking at I theta cubed over 3 factorial. Take out one of the i's, so it's I squared, which is minus 1, theta cubed over 3 factorial. Then look at the I theta to the 5. Take out one of the i's, so it's just I to the 4, which is 1, and it'll be 1 by theta to the 5 over 5 factorial. And that pattern goes on forever and ever. Now this is where the magic happens. The real part here, so the bit with the even powers of theta, is exactly the Maclaurin series of, that's actually the wrong way around. That's cos. that's sine. So you have the very, very powerful Euler formula. E to the I theta is equal to cos theta plus I sine theta. Now things are a little bit better. The problem now still is you still have a complex number. So you can do kind of cool stuff here. If you put in theta equal to pi, you end up with the formula. So if you put in, so weird kind of stuff that mathematicians will do is vote on most beautiful formulas, and this usually always wins. E to the I pi plus 1 equals 0. Combining 0, 1, e, pi, and I. So as a mathematician, that's a beautiful thing. Now we need to come back to earth. So we know now what to do with this thing. E to the p plus I q t. From before, we have the e to the pt. That bit is fine. And then what's the other bit? Well, it's going to be cos qt plus I sine qt. Now that's still a problem because you've got a door and you've got complex numbers, but something nice happens. So what you get is, so you can take out the common factor of e to the pt, because so the difference is going to be, so you're going to have one with the plus q, which is like the one I wrote just previously, and one with the minus q. They're both going to have an e to the pt. So you're going to end up with, let's see, a cos qt plus I sine qt plus, and is there an a missing there? There should be an a knocking around in here. Plus ai sine qt. Then the other one is b cos, and now you have a minus q. Minus qt plus b I sine minus qt. Right. So you can take some advantage of the symmetry and asymmetry of sine and cos to end up with this yoke. Now, we've used complex numbers all the time, but in any kind of problem that we do, of course, there won't be complex numbers. And it turns out that you can always find in a real problem values of a and b that make that a real number and that a real number. So basically what happens is, and we're going to just call them a and b, I think, is that the complex numbers basically just disappear. So we end up with the following. In conclusion, if the auxiliary equation has complex roots, then the general solution is e to the, now it'll usually be a minus here, but pt a cos qt plus b sine qt. All the complex numbers have disappeared. Happy days. Okay, now what about this yoke? Now, what's going on with this? Maybe we'll do this example here just to see this. Okay, so let's find the auxiliary equation. So we get 1r squared. Oh no, it said don't use r, we'll use lambda. So 1 lambda squared plus 1 lambda plus 1. So we're looking at lambda squared plus lambda plus 1 equal to 0. Now I put in the equal to 0 here because it's not simple to factorize this. So the a by the c gives you 1. And what are the factors 1 and 1? You cannot make 1 by adding these. So this has failed. When that happens in this chapter, and even in the next one, you'll use the minus b formula. So you're going to find that lambda is equal to, so minus b, now here the b is 1, so minus 1 plus or minus square root, b squared is 1 squared, minus 4 by a is 1, c is 1, over 2 by a, 2 by 1. Now what we have here is minus 1 plus or minus, the thing in the square root is square root of minus root 3. Now there's no real number that has, that squares give you minus 3. So we would have said this last week. If you see this yoke, you replace it with I root a. I put quotation marks in it because it's a little bit funky, but we'll drive on with it. So this is minus 1 plus or minus I root 3 over 2. And if you divide the 2 into both of them, you've got -1/2 plus or minus, now I want to get it exactly the right form, I root 3 over 2. So what we do now, so these are complex roots, they're distinct, but if they're complex, they'll always be distinct. You can't have complex repeated roots for technical reasons. Now, you don't have to go through all the vicious stuff we went through, the really cool stuff. You can just use this formula up the top. So we've got the p is equal to -1/2, and the q is equal to this root 3 over 2. So you end up with a solution. Now here, the function is r of t, so we'll use that. So r, general solution of t, is equal to e to the pt. So the p is -1/2, so you get e to the -1/2 t. Then form this bracket, a cos root 3 over 2 t plus b sine root 3 over 2 times t. Now, what we have to say now is that what is going on with these terms. So this term is a negative exponential, this goes to 0. But the thing in the bracket, sines and cosines, is a wave. Now you got a wave multiplied by something going to 0, so if you plot this yoke, it looks like this. It's what might be called an attenuated wave. That's a really good drawing by me, I have to say. Now that is an example, if it's a door closer, so you got the neutral position here of the door. I'll probably mess up my picture now. Pretty good. You can see that the door, say this is a door that's pushed open. At the peak it reaches its maximum displacement, and then the spring kicks in and starts pulling the door towards the door frame. Now here there's no door frame because the door actually swings. It goes from a positive displacement to a negative displacement. And this is a door, a swinging door, with no door frame, where the door, when you let go, it goes through the door frame and then it comes back, and it does close eventually. The oscillations get smaller and smaller and smaller, but it's not really a good design because you don't really want this happening. So this is an example of something that's underdamped. Really, the damper should be stronger. There's no need for the oscillations here. Okay, so in summary, what we have is these three, and these this is the basics. Well, it's a bit of this. So if the roots are distinct, you got an easy solution, and this will usually correspond to overdamped because one of them will go to 0 faster than the other one. So that's the door that closes fast and then slow. The bottom one then is underdamped. You have oscillation, so really more energy could be taken out. And then the one in the middle, it doesn't have oscillation. So the door, and of course, the thing with an underdamped is if there is a door frame there, the door will slam. This one now, it doesn't slam because there's no oscillations, and there isn't different speeds in exponentials. So it closes quickly, not quickly and slowly, just quickly, but it doesn't slam. So this is called critically damped. Critically damped. Right, and that's our, yeah, we've done it. That's a long enough lecture.